And yeah, according to the interview, Jeffrey started his career as the purest of the pure mathematicians, and it took him a couple of years to realize that also the application side of math can have some interesting aspects. And in a collaboration with Jill Pfeiffer and Joseph Silverman, he created the today widely well-known crypto system called Entru, which is based on lattices, and this happened already in 1995. But believe me or not, as I already mentioned, Entru wasn't accepted by the crypto community immediately. So it took another couple of years until the authors could finally convince the community that Entru is a great stuff. And today probably we cannot imagine modern crypto without Entru. So today Jeffrey is here and going to give a talk on his latest work on the multi-signature or aggregate signature scheme called MMSet. And thank you for agreeing to give me this seminar, Jeffrey. And now the screen is yours.
Okay, thanks. Could I encourage anybody? Oddly enough, it's a little weird for me. I can't see anybody. So I don't know if I'm going to have the slightest idea if anybody wants to ask a question. I don't know if it's even physically possible. But if it's physically possible, if anybody wants to ask a question or say, you're talking too fast, would you slow down, damn it? Please let me know, okay? It would make it much more fun for me. So let me just explain what I'm talking about. Just last year, almost exactly a year ago, excuse me, I was asked a question about signatures because it happened to come up in the context of blockchains. And the question was this: people sign documents, and there were ways if you took a whole bunch of documents that were signed with a single public key, you could sign you could sign a collection of all of them. But there was no way at that point of taking like 10,000 documents, all of them signed by different people with different public keys. And the objective was find some method of signing that block, that whole collection of the completely unrelated messages, and doing it in such a way that the single signature implied the validity of all the signatures of all the things that you were signing. In other words, you've got 10,000 different signatures, and you don't want to verify the public key, private key on every single one of them. You want to smush them all together into one thing, sign and have that one thing be checkable. And if that works, you're sure that everything works. So that was the idea. That was what we were aiming for. And it happened that in 2014, Jill and Joe and I and William White and another person named John Schenk had used rejection sampling to improve a scheme I had thought of quite a number of years before that had a defect. We had pass RS, it was called. That's pass for the original signature scheme, and the RS stands for rejection sampling. And as I was just telling Veronica, rejection sampling was a brilliant idea introduced by Lubashevsky to take signatures that are made out of lattices and make them impervious to transcript attacks. It used to be possible to take a long transcript of signatures based on a lattice, and then from that transcript reconstruct what the secret key must be. But you do rejection sampling, you could actually prove there's no information on it. And the scheme, the original scheme pass RS was based on commitment, challenge, response. In other words, you commit something, you get challenged, you mix together the commitment and the challenge, and you spit out something that has got a certain number of properties. And what you're doing is using a trapdoor to solve a closest vector problem. It could also, if you feel like being fancy, which I don't, view it as recovering a function from partial information about its Fourier transform. Well, but I'll skip over that part. So let me tell you what the characters are. Actually, Jill told me that you do the objects first and then the parameters. So I got those. So look at the objects first. So the objects are what is kind of the general n-true ring. You take z mod qz, if q is a prime, of x, you mod it out by x to the n minus 1, and then you take two polynomials in there and you multiply them in a way that you're probably or possibly familiar with already, a convolution multiplication, which consists of, as you can see, what c sub k is equal to in the last line. It's like you take f and look at a vector, g is look at it as a vector, and you take the dot product of it. Except you think of the vectors as circles, and you take a dot product of the circle with another circle. Then you rotate one, take a dot product, rotate it again, take a dot product, and you get this convolution multiplication. And then, but you do throw in something extra. What q is related to n in a way that it's equal to, for example, 2 times n plus 1. So that's the old Sophie-Germain problem, I think. You know, when you have a prime such that twice that prime plus 1 is also a prime. Well, you like to use that situation. It doesn't have to be 2. It could be any even number at k times n plus 1. But you would need to use a prime. We need the dimension n and the q to be related by that kn plus 1 approach. Okay. And then, here we go. What was the signature scheme? As I said, 2014. Well, here's how it goes. Suppose you take, I just explained how you multiply polynomials with this, but polynomials have other things you could do with them. You could actually evaluate the polynomials at certain points. And when in the world is it going to happen that if you take f and you evaluate at alpha and g at an evaluated alpha, you get the convolution product evaluated at alpha. That's not going to happen all the time. And the point is that alpha has got to obey the rule that alpha to the n equals 1, because the n-true ring basically sets x to the n equal to 1. And that, so you've got to do that. And as you can see from the rest of the slide, I won't go into it too much, alpha, if you take any alpha at all, then you raise it to the k power, that will always have the property that if you raise that to the nth power, you get 1 mod q by Euler's theorem. And there's a bunch of those. In fact, there's n of those alphas, the alpha to the k's that will do the trick. So you've got alpha to the k, alpha to the 2k. They all have this neat property that if you raise them to the nth power, you get 1. And that means they have that neat property that f of alpha times g of alpha will equal f multiplied by g times alpha. And so what do? You pick a bunch of these things. It doesn't matter how you pick them. You could pick them any way. You could pick the first t of them. You need to take about n over 3 of them, or n over 2 of them. You start getting down to n over 4 of them, and it starts getting insecure for various reasons. But you take about n over 3 of them, and you make a set of those, and you call them that omega. And they're alpha 1 through alpha 2 through alpha t. And so t is this number. That's the number of points that you're going to be evaluating it. Like I said, it's about a third of the dimension usually. And so as you can see, you've got, it obeys the product rule, and also, of course, it obeys the addition rule. So if you look down there, you'll see that the mapping, if you go from the n-true ring into t copies of z mod qz by the method of taking a polynomial f and evaluating it at t different places, that's actually a ring homomorphism. So that's quite amazing. In other words, like I said, f times g maps to exactly the image of f times the image of g, where the multiplication is component-wise on the right, but convolution-wise on the left. And addition just works like regular addition. Any questions so far? And am I talking too fast? I hope.
It's all good.
What's that?
All good.
Okay, great. Okay. So how do you do it? This is the fun part. So you choose, how can you set up a trapdoor? Well, it's really simple to set up a trapdoor. You just choose a secret F polynomial, all completely at random, that just has coefficients that come from -1, 0, or 1. And I like to call those trinary, but nobody else does. They call them trits or some, I don't know. Anyway, trinary just never caught on. But anyway, it's got coefficients that are -1, 0, or 1. And that means they're short. If you think of them as a vector, they'll have a length which is about the, roughly the square root of n, or the square root of n over 3. And that, if you take that f, it's going to have a bunch of valuations. And if you see that f hat omega, that's my convenient way for not having to write down that vector on the other side in blue, the f of alpha 1, comma f of alpha 2, comma f of alpha t. Okay, and now here's the thing: there's going to be exponentially many f prime with the same collection of valuations as that, because after all, you're only making n over 3 choices, roughly. There's quite a few that'll do that. But you could ask how many will take on these values and also have the fact that their coefficients are small, and they don't have to be less than or equal that. And I call that the infinity norm, less than or equal to 1. I could even say, how about infinity norm less than or equal to 2, or less than or equal to 3? Probably, in all probability, there's just one unique thing that has those valuations and is also small. And it's possible to set up a lattice problem where if you did proper lattice, if you were able to do lattice reduction, find a close vector in a lattice, then you could solve the problem of given the valuations f of alpha 1 through f of alpha t, actually recover the original f prime. But that's very hard to do. And the point is, it's quantifiably hard to do. So what do you do then? So how do you sign? Well, you take a hash of a message, mu, and then you choose something uniformly and randomly from -k to k to the n. So what you do is you take a k that's less than q over 4. This is where I wish I had a board in front of me and I could just wave my hands around, but I can't, unfortunately. But if you think about it, if you take a random vector, a random uniform vector from R, its coefficients will be random and uniform between -q over 2 and positive q over 2. So if you restrict your thing to be between -q over 4 and positive q over 4, that's quite a significant restriction. So in other words, it's highly unlikely that if that's something chosen at random would be in there. But you choose one uniformly and randomly from something like that. And then you compute a commitment. That is, you evaluate those y's at all of those special values, h sub t, at alpha sub t. You don't reveal y. And in fact, you don't even reveal the commitment yet because you're not sure you want to. But now, here's what you do. You create a really short, sparse polynomial by taking a hash of the commitment and the valuations of f that are, those valuations of f are, by the way, the public key. Forgot to mention that. So the valuations of f are the public key and the actual f itself is the private key. And similarly, you take the y hat and that potential commitment and you hash it with the message and you hash it with the public key and you get a really short polynomial. And when I say b1s and b-1s, I mean like say b could be 14, t could be 1,000, but b could be like 14 or so. And so when you multiply f times c, the very biggest any coefficient can possibly get is 2 times b, because that would be if magically every single one of c happened to hit something of f of exactly the opposite sign, of exactly the same sign, and they all added up together at a coefficient to give you 2b. But 2b is the biggest. And now here's what you do. You compute, you take f times c, the convolution, and you add it to y. And then you check, does it lie someplace? Does it lie within a certain boundary of that region? And let me skip to the next page. I want to show you the boundary. See, you see what I mean? The sides of the square are minus, let's say the top and the bottom, or remember, I'm talking about an n-dimensional thing. This is only a two-dimensional thing. So any dimension, it really should be 1,000 more dimensions, but it's hard to do. And if anybody was ever able to guess what f times c was, they would be able to recover y. And that would be a disaster, because you give out, in other words, the potential signature is that z, which is f times c plus y. And the idea is that when you're given the signature z, you're not supposed to be able to figure out from that what f was and what y was. And is that the case? And it happens that if it lies in a box like that, away from the edge, then rejection sampling proves that z contains no information about y and f. And if it doesn't, like if that box was pushing over to the side and overlapping, pushing past the boundary, then you would be out of luck. Okay, anyway, if it lands in the right place, you accept it and you publish that signature and your commitment, and of course your public key and the mu as a signature. And if it's not, you choose y again, and you try again, and you try again. And you can make it so the probability of acceptance, usually you aim for about 25%, but if likely to do it. So you have to sign about 4 times in order to get it to work. Okay. And then, and what's the idea? Why does this sign it? How do you verify it? Well, look, z is f times c plus y, so you've got to do 2 things. First of all, if you take f and you multiply it by c, that's small, that's short coefficients. If you add it to y, that's got short coefficients. They're less than q over 4. And so when you add it to z, the resulting coefficients are still less than q over 4. And that's short. So you're finding a short polynomial z, and then if you look down at the bottom of the screen to point 3, you'll see that for each alpha I, z of alpha I has to equal f of alpha I times c of alpha I plus y of alpha I for each of the i's. In other words, knowing the values of f and c and y means forces the values of z. And that's again why being a ring homomorphism is so important. It's multiplication and addition of these vector / polynomials are going into that. And so the verifier first checks that the z is small enough, then it recreates the c from the hash of the commitment and the message and the public key. That tells it what c is, then it could evaluate c, and then it finishes doing the check. And so what's the hard problem? The hard problem that the scheme is based on is, again, finding a polynomial that satisfies 2 conditions: that it has a short infinity norm, that the coefficients are not too big, and that it takes on a specified collection of values. So now come to the new idea. Let me see where I am, okay. Now we come to the new idea. How can you take a whole bunch of totally unrelated signatures and smush them together in some way that you could just validate one thing and that'll do it?
Can I ask a question before we move on?
Yeah, please, go ahead.
So for this problem that you mentioned, yes. I think you called them one-dimensional sys in the paper.
Call that what?
So do we know that it is, let's say, like
one-dimensional
sys, or do we know of any certain relation to sys?
I'm still not quite catching the question. Say that again.
So for this problem that you mentioned before, the problem that the security of the signature scheme relies on.
Yes.
Do we know whether it's strictly easier than cis, or whether it might be as hard as cis?
Short. I was mishearing the short integer solution.
Yeah. Sorry.
Yeah, sorry. That's another problem I have with cryptography. It's got more acronyms per unit paper than imaginable. It's not really. It's actually sort of slightly. Yeah, it's related to that, but there's no ring homomorphisms that go on. It's basically it is built on a short integer solution type of problem, but it's built in a different way, taking advantage of a previously existent ring structure. The relevant lattice that is based on or matrix is a Vandermonde matrix. So it could be called related to a Vandermonde SIS problem.
Okay, nice. Thank you.
Hey, let's see. But the point is, there's extra structure here, and it's the extra structure that allows you to do things that I like. So now I wanted to say, how can we save space? So I want to mush things together. So how can you save space? Well, remember, you created C using a hash of all those commitments and the message and the public keys. Now it takes a long time, a lot of space to store all those commitments, and each one takes T times the log base 2 of Q, because there's T values, and each value takes log base 2 of Q bits to store. So why don't you take a linear transformation on a T-dimensional space and map it down to a T0 dimensional space? In other words, just sort of squash it while preserving a linear structure. Then depending on how small the dimension is, it doesn't require too much bits at all. You could just take T, you're just taking the T dimension, you're taking a T-dimensional vector space and projecting it onto a T sub 0 dimensional vector space. Why not? And of course, there's many different yi hats omega that can go down to a particular image, but your chances of accidentally choosing two things that go to the same image are completely negligible, small enough to ignore. So if instead of just keeping track of the whole commitment, you compress it like that, then that works out quite nicely. In fact, then you could choose it so that the number, how the amount of space it takes is T0 log base 2 of Q, namely whatever your security parameter lambda is. Like let's take lambda to be about 128. So that's much smaller than the other one, because T would have been n over 3. If n is about 3,000, or that would be 1,000 times whatever log base 2 of Q, and that could be in the 100. That could be about 60 or something. And so anyway, it gets quite big, and so this saves quite a lot of space. And now, how could we go about almost did we do before? When we selected the challenge polynomials, we hashed, look at the top line, the whole y sub I hats, but now let's hash T of the y sub I hats and the mu sub I and the f sub I hats. Okay, and that's how you generate the C sub i's now, the challenge polynomials. And now comes the next step. What are you going to do now? You've got a whole bunch of stuff to combine. And why not take all of these polynomials, C1 through CK, and hash them together into a string of beta 1 through beta k. Just, that'll determine it. And then, bingo, this is it. This is how you aggregate signatures. You just take that linear combination that's forced on you, that's determined on you, and you create beta 1 z1 plus ... up to beta k zk. And this is, and it's because of this that having a ring homomorphism is going to turn out to be so extremely important. So that's that second line from the bottom, or third line from the bottom, is the key thing. What you're doing is you're just doing something as stupid and simple as just adding the signatures together. You actually could, even if you felt like it, you could leave out the betas and just add the signatures together, Z1 through ZK. But there's various reasons where, for technical reasons, it's kind of handy to have the beta 1 through the beta k come up arbitrarily, and I'll explain them later. But I don't think they're not really there for security. They're there for convenience. Okay, and now, but how in the world are you going to validate this in a convenient way? Well, to validate this in a convenient way, well, remember we had those commitments that we had before. And if you're aggregating signatures, you are now an aggregator. You're a blockchain. You're somebody taking part in a blockchain, and you want to be one of those people that creates the next block. And so you take a bunch of transactions. You look at the collection of y sub I hats, and you generate all those. You generate all those c sub k's the way I just said, and you use the c sub k's to generate the betas. Where am I back? Yeah, remember the ci's come from the hash of all those things, and then the betas come from the hash of the ci's, and then you've got these betas to do the linear combination, and then you use exactly the same betas to add the commitments together to get a big capital Y commitment. And what can you do with this big capital Y? For one thing, as you can see from item number 1, it's certainly going to be true because capital T is a linear transformation, that capital T of Y is equal to the linear combination of the beta i's, kind of the capital T of Y sub I omega. And that shows that with extremely high probability, your Y, capital Y, must be related to the little t of y sub i's, because it would be, if parameters are set, it's quite hard to find the collision here. And then here's the thing: how can you check that Z has the correct value? Well, you can check that Z has the correct value by what? Look at what are the values of Z supposed to be? Well, Z is equal to the sum of with the beta coefficients of all the Z's. But if you look at line 2, that's exactly what's going on. That circle dot means component-wise multiplication. So in other words, you're taking your capital Z, and you are adding up all the beta I values of f of i's times the values of the c i's, and then you're adding the y's, except the y's are all added together already into that capital Y. And so there you go. That's part of the verification. Again, I apologize. I know it's much more typical in cryptography talks for me to throw up an algorithm on the screen and write the whole thing in pseudocode. But I just don't think, what I did to create these slides was to translate English sentences out of pseudocode, because I happen to personally hate pseudocode. Anyway, so you can check that the Z has the actual correct valuations, and you're doing this valuation in a place, well, I guess that doesn't matter much now. You're doing it in ZQ of T. Never mind, it's not tremendously important. I'm probably confusing. But anyway, there's a lot of symbols that's been going on, and so I thought it might be a good idea to have a summary slide that tells us where the heck we are at the moment. And so we have so we started out with K signatures. So each of them originally had the form a ZI and a YI hat and an FI hat and a mu sub I. So we had K of those 4 tuples of objects. Now, what does the aggregator do? Well, it takes capital T of all the y sub i's, squishes them down, which saves space. Then it computes all the c's from the hashes of the t's and the mu i's and the fi hats. Then it computes the beta from the hashes of the c's. Then it creates that capital Y by taking the linear combinations of the y hats. Then it takes the final signature by taking the linear combination of the zk's. And the final aggregate signature, well, actually, this is the semi-final aggregate signature, is down there. What do you have? You've got z. That's not too bad. That's n, dimension n times log base 2 of q, roughly, is, you know, log base 2 of k, of little k, really. There's capital Y. That's a kind of pain in the neck. That is t times log base 2 of q bits to store. But then you've got a bunch of things that don't take really terribly much space to store. You've got the mu sub i's, they're not long. You've got the capital T's, the yi's, they're pretty squished. There's just one pain in the neck left over, this fi hat, the public keys that are still there. And those public keys are really, are just long. The public keys, each public key is as long as that single Y. So unless you could somehow compress all these public keys as well, you're really not going to be left feeling too satisfied. But before I go on, how do you verify an aggregate signature? Then again, let's go back over it. So that up on top is the aggregate signature. There's the Z, Y, those are the various things. What do you do to verify? Well, first you recreate all the C's, vary the hashes. And here's an important thing for security. You have to check that they're all distinct, all the CIs. Otherwise, there's some very sneaky things that an attacker can do by throwing in something false with their own public key. But if all the CIs are distinct, that's pretty good. And then you recreate the beta. And then what do? You create something which you're going to use to test your capital. You're going to use to test your final capital Y. In other words, you're given all these capital T, compressed capital T's of the yi's, you string them all together with the beta i's and make W. And then you compute Z. Now Z had better be all the valuations of the final signature Z. Capital Z had better be the list of all the valuations of the capital Z. Because remember, the capital Y is all the valuations of, is the sum with betas of all the other things. And I'm reminding you that, remember, capital Y is that linear combination of little y's. And that W is that sum of the beta I capital T of y sub i's. And the Z that you just constructed is supposed to be on number 3, is supposed to be this. So what has got to be true? It's got to be true that T of Y reduces you down to W. Because if it doesn't, something's wrong. And it also has to be true that this capital Z, all the valuations of that match up with all the valuation. Well, you're given Z, and so you can compute all the valuations of Z, and that had better match up with all the valuations you've gotten out of this thing. So by the way, if you're actually keeping track of all this, then you're much smarter than I am. That's why I sent the PDFs over to Veronica. You can go through this later and double check it. But basically, what have you done here? also, what's the point? The coefficients of each of the little signatures are uniformly distributed in this interval. And when you add all these signatures together, you're taking a random walk. And each walk is length plus or minus k minus 2b. And when you add them all together, when you add k of these signatures together, then with extremely high probability by the central limit theorem, the infinity norm is not going to be bigger than a constant multiple of the square root of the number of signatures. And you choose the b so that you're right, so that it works most of the time. And by the way, that's the main reason why the betas are there, because there is a certain amount of oscillation. But if you're aggregating, your signature turns out slightly too big, you could just feed them in a different order, get a new set of betas, and the chances are pretty good that that'll work then. Okay. Oh, sorry. So that's the end of that. That's verifying. That's how you verify the aggregate signature. Now here's the last crazy thing. Do I have time? Yes. Good. Just bear with me. Almost here.
Can
yes.
I ask another question?
Please, please.
Could you go back 2 slides, I think, where you had the signature output, the final signature output? Ah, yeah, this one.
Yes.
Ah, yeah, or this one. Yeah. So here, so do you know roughly? So I think, for example, if you don't publish this T of Y hat eyes,
right,
and if you publish Z eyes, I think you can construct Y eyes from the information that you have. So what would be size?
Wait, hold on a second. What did you say again? If you
instead of publishing,
you're saying don't publish the capital T of Y sub i's.
Yep. And instead publish the Z eyes.
The Z I. Oh, of course. If you publish the Z I, then sure, everything is recoverable. But the point of this aggregate signature is you don't want to list all the ZIs because that takes up too much space.
Yeah, I was going to ask, like, what would be the size of ZI versus the size of this T of Y hat eyes? So these T of Y hat eyes are much smaller than Z eyes?
I actually have a table at the end which will tell you something. But let me give you yeah, well, great to have a whiteboard here. But here's the story. A capital Z is n components. Each component is an integer. Is some integer roughly between minus q over 4 and q over 4.
Mm-hmm.
Okay, so that's log. So it's which is so close to log base 2 of q as to not be too different. So the size of it, the size of a z is roughly roughly n log base 2 of q.
Yeah.
Now, how on the other hand, the size of a single y of a single t of y sub I is 128 bits.
Ah, okay, I see. Ah, yeah. That was the whole goal for this.
That's the reason. We're trying to whittle everything down into the minimum possible information that we could use to actually reconstruct all the information.
Okay, yeah, I see. Okay, thank you.
Okay. Let's see. Okay, so I was doing that. Okay, and now here comes here's the part that I kind of like. Create your, how do you, in the world can you compress the public key? So what do? Well, remember we squashed the y sub i's with a t. We've got capital T of y sub I. Well, let's also squash the f sub I hats. Let's also squash the public keys. Okay, and now I'm going to change it to the hash so that the CIs, the challenges that come out, are a hash of not just the T of yi, not just the mu I, but also the hash of the T, that also the T of the squashing of the public key. So you've got one of these for all k. And now, what do? So you're computing Z, And then the aggravator picks T prime. Now T prime is a really small number. T prime is going to be like 40, okay? T is going to be like n over 3. T is going to be like 1600. T prime is going to be like 40. And you want to pick a T prime, a number T prime, such that two combinatorial conditions are met. And the most important is the right-hand one, that the ways of choosing, the ways of making T prime choices out of T is bigger than 2 to twice your security parameter. But that really happens fast. It's even if T is pretty big and T prime is about 40, you're already there. And here's what you do. You take a hash of, look at the bottom line, what are the last really serious pieces of information you have left? You've got your Z, which is the sum of all the little z sub i's. You've got your capital Y, which is the sum of all your commitment Y values. And then finally, you've got all these C1 through CKs that come out of hashing everything in existence. And you hash together that, and out pops a subset of omega of length T prime. A completely random subset of omega with T2 prime. So omega might have 1600 elements, and then a hash function chooses a subset of, say, 40 elements out of this T prime, out of this omega. And now, what's the final signature? The final signature is then the Z, the Y, the mu i's, those are the messages. Then there's the squishing of the Y commitments. Then there's the actual genuine Y sub I commitments. But those are much smaller because those are Y sub I hat slash omega prime. That means for every Y sub I, you only have about 40 mod Q values, as opposed to 1600 mod Q values. And then you've got the squashes of all the F sub i's, of the values of the F sub i's. And then the public keys, you save only the parts of the public key valuations that correspond to omega prime. In other words, you originally had a gigantic collection of valuations that your polynomial Z signature had to satisfy like 1600 valuations. And now you're choosing 40 valuations or something like that out of it. But here's the thing, the choice of the 40 is depending upon everything else, including Z. Now, suppose you were trying to set up a lattice reduction problem where your output is going to depend on your input. It's, in other words, where you're trying to find a short polynomial that had specific evaluations at points where the points depend upon the short polynomial that you're looking for. It sounds hard, and actually in our paper we've got a pretty precise analysis of showing that not only does it sound hard, it actually is hard. And so, and let's see, where am I? Yes, and so that's the idea. And so, so the aggregate signature, when we're down at the bottom, where are we? Well, we're n log base 2 of some constant times the square root of k times k. So what's that? That represents the size of z, of little z. That's the size of everything you added together into one signature. And then what's the t log base 2 of q? Well, you see the capital Y up in the top line? That's how much that takes. That's y is t different log evaluation, t different valuations, where each valuation takes the log base 2 of q bits to store. So the little z and the little y take up the first 2 terms down to the bottom, and everything else is so trivial that it all roughly gets mushed together into twice. You have to have one of those for each signature, but basically it scales. It scales linearly with the security parameter. So, so for example, so here's an example. So, if lambda is 128, we tend to use, say, n is 4349. If k is 10,000, q is 2 to the 26.6. Then it turned out like t is 1449. T prime was 40. And so one signature takes that, and 10,000 signatures takes, so as one signature plus another 10,000 times 128 bits, roughly. And it becomes that asymptotically as it gets bigger. And oh, I wish it, can you see my screen here? I just widened it, I think, a little bit. This tells you, this compares this to various other schemes out there like Bliss. The other things don't actually amalgamate, don't aggregate themselves. So, but if you take a look, you see MSAT, MMSAT, just look at the 128 one. If you could aggregate 1,000, 5,000, 10,000, then if you look at the far right, don't bother with the uncompressed. Skip the middle section. This aggregate signature size, that's how it is. That's how big it is. And compressed public key size turns out to be that big. And if you compare that down at the bottom to, in the middle to the ECDSA, there's not really terribly much difference. And so, in other words, it's a way of, you know, if you do this for one signature, it's kind of clunky. But asymptotically, the more signatures you pour on, the more it turns out to be like ECDSA. And I think I said quite enough.
Yes, thank you very much. It was very interesting. Now, now questions from the audience.
Okay, may I ask a question?
Yeah.
Go ahead.
All right. So I am aware of pass encrypt as well. Okay.
A pass and what?
Pass encrypt. The scheme.
Oh, pass encrypt.
Yeah.
Oh no, you don't use pass to encrypt anything.
Yeah, I know.
Oh, we did write a paper with pass encrypt. You actually read that?
Yes, I know about that paper as well.
Oh, wow.
Yeah, so my question about, once comparing pass encrypt to these pass RS is that here your recommendation is to choose omega to be n/3. But in pass encrypt, you talk about n/2.
Yeah, and you're wondering why the difference?
Yeah, why are you going that direction? Is there any problem?
The reason is that lattice reduction techniques have been honed and changed an awful lot since we wrote that paper, and when we chose n/3, we were balancing we were balancing a couple of different things. Basically, the smaller you make T, the more efficient you become, but the weaker your lattice security gets. And the very strongest lattice security comes at n/2.
Okay.
And so we chose that for pass encrypt, just to be conservative. But here, with all these measurements that people have put out, the ways of measuring, you know, figuring out block sizes and ways of doing things, we figured we might as well hone in as much as we possibly could, and we found that n/3 came out, as pretty much the winner as a good place. N over 4 turned out to be too small, weirdly enough.
Okay. All right. So I've got another question.
Yes.
So can you please go back to page 19?
Yeah. I think I can. Let's see if I can. Okay. Okay. Tell me where. There's 19. Okay.
Yeah. So these two conditions that you want to satisfy with respect to T prime.
Yes.
So so the second one that you said it's more important one. Is it why do you want to satisfy this? Is it because you want to prevent like dictionary attacks on omega prime, or what?
It's because you don't want the most obvious way to attack this would be you see, the problem becomes easier the smaller the number of values are.
Yeah.
And we're jumping down to a pretty small number of values there. So we want the number of values to be as small as possible, but we want the chances of somebody hitting those number of values, that collection of values at random, to be as small as possible. And so choose T prime being bigger than 2 to the 2 alpha means the chances of that's being sort of conservative. If we were being more or less conservative, we'd say 2 to the alpha, 2 to the lambda. I mean, but we're choosing something that if you just we're making a list, just making all sorts of choices, the chances of even colliding your list is probably pretty small.
And combining these two conditions together, so you get lower bound and upper bound on T prime. How large is the
upper bound on T prime is T. I mean, you don't have to do this at all if you want to waste a lot of space. But right. It's most fun to make T prime as small as possible, because because the public key is what really drags you down here. So it's nice. So we've accomplished this aggregating by basically close to doubling the size of a single key. Because if we were to do this for one signature with pass, we could do the signature, and we wouldn't even have to do the valuations of y. We could actually just do the challenge polynomial C, and then people can reconstruct y from C, and then do all the checking. But here, in order to get this to work, we had to, irritatingly enough, not give people the C's and have them reconstruct the long Y's. We had to give them longer Y's and have them reconstruct the shorter C's. So, but thank God we only had to do it once.
Yeah.
So.
Okay, thank you. I let others to ask questions.
Yeah, can I ask also a question?
Yeah.
So this, if we make this analogy between the Vandermonde CIS problem that you are using here,
yeah,
and the standard CIS problem, so it seems that your approach can be instantiated also in the random CIS case, right? Rather than this Vandermonde one. So have you looked at?
Well, in the what case? Not rather than the Vandermonde.
So if you replace the Vandermonde matrix, which evaluates at these roots, if you replace it by a matrix over ring elements, so you just do you know like the ring CIS problem?
No, I haven't thought about that. But can you get up? The important thing here is not the short integer solution stuff. It's the duality between functions and Fourier transforms of functions, and the different types, and the fact that in vast generality, the mapping from a function to its Fourier transform is actually a ring homomorphism. So in any place where you could instantiate that, you have the possibility of doing something interesting. So, but of course it becomes totally uninteresting if you do it in a continuous setting. but it becomes quite fun and interesting if you do it in a discrete setting like this. So in these van der Waals type rings, I'm really not familiar with it at all. But can you associate with that with any sort of evaluation process? Yeah, I'm not thinking of multiplying matrices by vectors here. I'm thinking of you know, the really quite different notion of actually evaluating.
Yeah, but I'm wondering if this can generalize to more general matrices than just the van der Waals.
Yeah, I wonder too. Somebody actually sent me an email about that a couple of weeks ago, asking the similar thing, and I had to reply the same thing, that I think the connection to the van der Waals SIS is a coincidence, and the generalization doesn't go in that direction, but I'm awfully shaky and uncertain about that. I'm not at all sure that I'm right in saying that.
Okay, yeah. All right.
So I'd be very, put another way, if you have some thoughts on that and feel like mentioning them, I'd be very interested to hear.
Yeah, sure. Yeah, we'll think more about this. Yeah, thank you.
Okay. Any other questions?
I think we have no more questions, and it was a very good presentation, I must say. And
yeah, thank you very much.
A very good presentation. You're afraid?
no, I must say, I'm not afraid. Oh yeah.
Yeah, thank you. It was very good.
Okay. Well, thanks. And one quick question: Are you guys all holed up where you are, or are you wandering around?
We are in Melbourne. We are still in lockdown.
Yeah, because I've been locked down in my house since the middle of March now. It's really
Already same for us.
okay.
Yeah.
Yes, actually, I kind of enjoy it.
Really? But I think I'm getting already tired of it.
Yeah, you know, usually I have this feeling, gosh, I haven't accomplished anything today, but now I don't have to worry about that because I can't.
No, I think today you have accomplished something. Yeah, you made a great presentation, really. It was very understandable for, I think, for most of us.
Okay. Thanks, and I would not be at all surprised if anyway, if you actually, I know that I couldn't have followed this if I was explaining it. So if anybody is actually interested, you should read over. Like I said, I emailed the slides to Veronica, and please take a look at them.
Yes.
Okay.
And maybe we will get back to you via email if you have any questions.
Yeah, so we'll write back with questions. Yes.
Yeah.
All right. Well, thanks very much, everybody. It was awfully kind of you to invite me.
Okay. Thank you very much.
Thank
you.
Bye.
Bye-bye.
Bye.